welcome to the session on Loopy and Unloopy programming techniques. Just as a general introduction, this is kind of, I was in on the intro to NumPy session, and this is in some sense like an advanced NumPy session. I'll explain more about what I mean by these unloopy programming techniques, but generally I mean vectorization, the kind of thinking that you had to do NumPy. I'm going to organize this in terms of, oh, you know what, you should first. This, I believe, is, everybody has access to this link, right? You all have this and you're looking at it? I posted it on Slack earlier today, the Slack for this session, so that should help you to find it. So we'll get on the same page, literally, the same web page, and then we'll go from there. Okay? Yep. And to do these exercises and to be following along with me, you can. I encourage everyone to run this on Binder. So you can install everything on your computer, but that's up to you. There is a requirements txt, which is what makes the Binder work. And you can get these packages, not necessarily these versions, but I pinned all of these versions so that this tutorial is repeatable. Yeah, and so the rough outline will be like this. I kind of took the material that I had and divided up by the time. The main part of this, the part that we really want to be sure to get to, are the exercises. And in this, actually, I'd like you to pair in groups of 2s and 3s. You know, whether they're 2s or 3s doesn't matter, but make groups, except for the helpers who are floating around. Yep. So yeah, make groups, get to know each other. Hopefully, actually, during these exercises, this will be a noisy room. Hopefully. 2s and 3s to solve the what if we have an odd number of people problem. Yeah, so sit near each other. And also, I will adjust to the level of the room. You know, if everybody's having trouble, then I'll go more slowly. If everybody's just whizzing through it, then I'll do all the material. I prepared more than enough material. So if this looks like a lot and gee, how are we going to get through all of this? Don't worry. That was kind of the point. It was in order to have this kind of flex. Okay. So to get started, in order to be able to follow along, click the Launch Binder button, or if you want to be able to get back to GitHub afterward, you know, open in a new tab. And that should open this up rather quickly. So so I'm going to wait until everybody's on the same page here. So raise your hand if you're not, if Jupyter's still loading, and we'll watch the hands go down. Okay. So you're watching the screen and you see all the stuff loading, loading, loading. So everybody's hand is down. You all have a Jupyter notebook up. And since this will probably come up, if you don't touch Jupyter, if you don't touch Binder for a while, it might log you out. You might need to reload the page. Yeah, just reload the page. It will remember nothing. You'll have to, you know, run up to cell. You know that trick of select a cell and under kernel, or here, run up to the current cell, run all above selected cell, that sort of thing, to get back to where you were and be able to keep going. It will not remember any of the commands that you've done. So when you're working on the exercise, generally the solution to the exercise is going to be like a one-liner or a couple lines or maybe a little function or something like that. But if you don't want to lose what you're working on while doing the exercise, be copying it into a text editor to make sure it doesn't go away. All right, so let's get started. Just on the part that's not an exercise, just shift-click along with me. And if you want to try out different things, just try out different things. And if that leads to a question, so much the better. Raise a hand and ask. So Loopy and Unloopy. Here I'm talking about whether your code has explicit loops, whether you can see the for loop in your code. It's a programming paradigm. So I'll be talking about this paradigm called array-oriented programming. And the way that I'll be using the word, this is a paradigm in the same sense as paradigms like imperative or object-oriented or functional. Has anybody not heard of at least one of these? Imperative, object-oriented, functional? Yeah, okay, good. That's all you need. Just to know that there are these paradigms in programming. Bigger than difference between one language than another. They're kind of like one group of languages or a way of programming within a language. In array-oriented programming, make it big. There. In array-oriented programming, the primary data type is an array. And most of the functions perform one operation on all elements of the array. So, to give some examples of what it is not, this is not array-oriented, where here we have some input data and we're filling in output data by writing this explicit for loop and performing the operation one at a time, because this explicitly specifies an order of execution and you say what happens to each element. So it has a lot of control, but this is not what array-oriented programming is. This is imperative programming. You are telling the computer exactly what to do, imperative. Also, this is not array-oriented. Does anybody recognize this style? What paradigm would you call this? This one is a shout out. Yeah. Functional? I heard something else, but I didn't quite make out what it was. I would also call this functional because you make a function and you give it to another function as something to apply to it. And although there's no explicit for loop here, it's still, I guess what you would say, not coordinate free. You've explicitly, you've specified a coordinate. This x is one element. And the code here is describing what to do to one element. So that's how it's different. And by the way, there's nothing good or bad about a paradigm. It's not we should be always using this or that, except for certain purposes. So here, this is array-oriented. And if you're longtime NumPy users, you probably know this. This is, how you do basically all math in NumPy is you write a formula using the arrays as though they were scalars, but it applies to whole arrays. So here we get the output data as each output datum is the square of each input datum because we take the whole output data array and square it. So is this kind of a nebulous distinction? Yeah, because programming paradigms are kind of nebulous, and you can have long, interesting arguments about whether this something or other is an example of a paradigm or not. So they're kind of nebulous, they're fuzzy around the edges, but they're useful concepts to talk about a general direction. So I'll be talking about the general direction of array-oriented programming. And as a way to dive into that, this is one of the little-known paradigms. You'll hear people talking about imperative, object-oriented, functional, you'll hear about that all the time. But array-oriented has kind of gone under the radar. But it has been around for a long time. So I have been making this diagram of all the languages that I know to be array-oriented or have array-oriented features, and this is becoming a more and more crowded diagram as I learn about more and more, some of them quite obscure languages. But it all started with APL, and this is way back in the 1960s. It was named after a book called A Programming Language. It was early enough that this is what you say. And originally it was really the programming language. People did APL by hand. And when they started doing it on a computer, they wanted to use the same symbol they were using by hand, so it was special sequence. And this is, a great grand ancestor of a lot of these, and some of them you will have heard of MATLAB, simply NumPy. I'll get back to the general features of all that. APL, with its mathematical syntax, was ultra complex. Programming languages have not been getting more and more complex. Some of them have been backing off, some have not so far. Just to give an example, this was what some APL syntax looked like in the corresponding. Some of these flash there to reduce a range. And you could spend a very long time trying to get something to work in this. And you do, you put on a t-shirt. All of the array since the beginning. APL was like this. That was the whole idea of speakeasy, is that you're speaking to a computer. And these are languages for doing statistics and data analysis where one-on-one back and forth conversations with a computer is essential. So they were intended for users to tinker with experimentally. And in retrospect, this makes sense because data analysts are often asking themselves, what will this function do to the distribution of all data? Like if you applied a function to one element, that might not tell you anything statistically about what you've just done. You have to see the whole thing. So suppose we take like 1 million data points. First question you ask is, well, what does it look like? In this case, it's a normal distribution because that's what I generated. What would happen if we just squared them all? Try to get in your head, like, what's this distribution going to look like? It's a little hard to guess, but you can just try it, see what happens. And okay, it gets a longer tail, and it's always positive. Okay, that makes sense. If you just tried this on a single positive example, you wouldn't necessarily know that, they can't be negative anymore. Now, what if you do this operation? Take the sine of 1 over it. Just imagine, what is this distribution going to look like? And I couldn't tell you. I would have to think, sine of, I don't know. And if you had one value, it's still not really going to tell you what the distribution is going to be. Distribution is this cool thing. They pile up at 1 and -1 because of the sine thing. But, there's this bulge here, and it would take some serious thinking to predict that. But it's quick when you're doing it with a computer. So this is what array-oriented programming languages are good for. Do one thing to all your data, look at it. Another thing to all your data, look at it. So there's 2 advantages. The mathematical expressions are more concise, and so it's a convenient way to type interactively. Not as concise as APL, because that was a mistake. And the right part of the computation is accelerated, the loop over all the data points. You've got 1,000,000 data points. You don't want to have to wait for it to turn over all those million. You want to immediately see the answer. So you're here. You are familiar with array-oriented programming in Python, NumPy. You might be using this more often through Pandas. You might be using this more often through Xarray. You might be using this more often through JAX or PyTorch or any of these things. But this is the basic thing, and the syntax has been is mostly universal. So this quick reference card is the kind of thing you want to just sort of have in mind or refer to, and that sort of thing. So this is just display NumPy exists. Okay. Got it? All right, we're all good on NumPy. And about the interface, so NumPy makes arrays duck typable with scalars and mathematical calculations. This is the advantage that it's bringing, because Python has duck typing. Unless you specify the types and type check it, any types that will work in this expression can go through the expression. So let's take the quadratic formula. This is the solution to a squared plus ax squared plus bx plus c equals 0. This is that solution. If we put in a, b, and c as scalar values, it can go through the formula, give a scalar value. If we put in arrays, it'll just go through the same formula, give you an array. And then about performance, NumPy makes, and here's the important thing, NumPy makes each step in this calculation fast, but not necessarily the whole expression. And so we have other things for that, because that'll be actually another theme that's coming into this is about performance. We're doing this for convenience and for performance. So the quadratic formula above is essentially equivalent to the following. We want to compute minus b squared, 4 times a, and what NumPy is doing behind the scenes is essentially this. It does each one of these operations and makes a new array for each one of them. And then and uses, does each operation, makes a whole array, does operation make a whole array. And that's not necessarily the most efficient way to do it. So as a way of showing that these are kind of the same, this was doing just NumPy simply, and this was doing all of the steps individually, and they come out to be about the same. And I'm going to wave my hands about the less than 2 times difference. Okay. So 17, 22 milliseconds, something like that. There are other ways to do this, like you could take numexpr. Okay. numexpr takes this whole expression and evaluates that on each element in a single pass. And you'll see, if you're trying this out, that this is faster. If you're doing any operations in Pandas inside of quoted strings, you notice that that's faster. Pandas is using numexpr. It avoids all of the intermediate arrays in between, because it's great if you make an intermediate array and look at it, make another intermediate array and look at it, but if you're not looking at it, it becomes a liability in terms of performance. Another thing that we can do is we can actually compile it with like LLVM. Numba does that. So you're just want you to be aware of all these tools that you can use when you're thinking about performance. Numba can take a function like the quadratic formula and actually vectorize it, make the thing that that numexpr did. But whereas numexpr just has a fast virtual machine, this will actually compile it down into machine code. And it'll be a bit faster as a result. 16 versus 2. And JAX also has a JIT compiler. Numba.jit, jax.jit. Its JIT compiler is like quite different. So between Numba and JAX, we've got the basis states of oh my goodness, I'm using math terms I shouldn't. Between NumPy and JAX, we've got two sufficiently different things that it's worth trying them both. So with JAX, it really must be array-oriented. You can't go down to an imperative level the way that you can with Numba, but it does more optimizations with what you got. In this case, Numba is faster, but it all depends on the problem. Okay, so generally speaking, sort of to put an end parenthesis on that, carefully optimized implementation is out. Yeah, so what's fastest? Carefully optimized implementation, you get out C++ or Rust or something, and you really, you really do it right, and you get all the memory things out. Yeah, that'll be fastest. Compiled single pass loop is faster than a NumPy expression with all of its intermediate arrays, and that in turn is much faster than the Python for loops. So we've got this hierarchy of speeds. So you pick what's right for the application that you're doing. So now we're getting to the part that is going into the first exercise. I'm getting ready for how thinking differently about programming problems, thinking unloopy. And here the focus is on the way that this is going to change your thinking. The more you do this. If a programming language doesn't change the way you think, then it's not worth learning. That's what Alan Perels said. And this really does change the way you think if you are coming from an imperative world. So computing expression in which all the indices line up, like the quadratic formula, that's one thing. But it really becomes powerful. So take these numbers, and numbers minus numbers, you'll get zeros for every element. It really becomes powerful when you are doing things that shift indices and then you do some math. Like cut off the first numbers, cut off the last one, and subtract them. And this now the top aligns with the shifted bottom. And you can do differences between members of these numbers. So the numbers were 1.1, 2.2, 3.3, 4.4. If you do numbers bracket, if you slice off the first, subtract, slice off the last, you can find their between number differences, 1.1, 1.1, 1.1, 1.1. Things like that. So now let's get creative. How about taking these ones and add them with a slice? Okay. Now, you could make a triangle by slicing more and more off, adding and adding them up. These kinds of things. And you'll be using some of these kinds of things to do the exercises. Real world application. Oh, let's say that we've got some noisy data, and I want to smooth it. So I'm going to take the data, make a copy, and on the smooth thing here, I'm going to do that triangle trick. And each time, add it to its shifted self, divide by 2, that's taking a mean of each value with its neighbor. And let's do it again. Take a mean of each value with its neighbor. And please do, reevaluate this. Here, the original. And just slowly smooth that data. Because each element with its neighbor we're just sort of smoothing out. Now, I don't want to leave you with the impression that this is a good way to do smoothing. There are NumPy stride tricks sliding window view, which is super efficient. And also it has a flat kernel, whereas what I didn't exactly have a flat kernel. I didn't want to just jump to that because it's kind of like Deus Ex Machina. It's like, oh, there's this function that does the thing for you. But just think about it. You take all of the elements and their neighbor and just average them, and you can slowly smooth out a thing. All right, so now we go to the exercise. So click on the link to jump to the first exercise. And what you'll be doing here is Conway's Game of Life. Okay, so everybody, raise your hand. So all the hands go up. All right. Now, lower your hand if you've heard of the Game of Life. Okay, so Game of Life, now I'm going to introduce it. Game of Life is an automaton. It's a simulation. It's describing like the cellular automaton, like a petri dish kind of thing, in which there are some living cells and dead cells, and they're all arranged on a grid. And the live cells with fewer than 2 neighbors die, as if by overpopulation. The ones with 2 or 3 survive to the next generation. If there's more than 3, then it dies like overpopulation. And so any dead cell with exactly 3 live neighbors becomes a live cell, as if it was reproducing. So this petri dish, things reproduce, die off from being isolated, or die off from being crowded. And so by being sort of in the middle of that, you get these interesting patterns where things are able to spread, but they don't just flatten all over everything. It looks like this if you run it for a while. So you set up, you've got this cell, this grid of cells, and in each cell is either true or false, which will be black or white, the pixels on or off. And especially if you set up the initial conditions right, not only will it spread in interesting ways, but it can make these repeating like rocket ships and things. And there's a huge, lot of people have gone down a deep path of searching for interesting things in the Game of Life. It's just those rules that I've read out, but it's just full of interesting patterns. So let's set up a board, and the board is going to be NumPy zeros with a given width and height. So we're going to make just a 2-dimensional array. And you have to actually import NumPy. 2-dimensional array. And this particular pattern came from here because there are people who study these things. All right. So when we have this 2-dimensional array, we'll need a way to visualize it. You could use matplotlib and do that if that's what you're comfortable with, and you just pass this 2-dimensional array to imshow and you can see it. But what I'll be doing in the prep will be ASCII art, because this is very debuggable. And you can make variations on this that make it even easier to debug, which you might be needing in the exercise. So those rules that I described, here's what it looks like in an imperative implementation. And when you're working on the array-oriented implementation, you can look at the imperative as a way to, get in mind what you're trying to achieve, and it can help. It's easier to read than the 4 rules, I would say. Because this is imperative, this has to build up a list of lists. It does it by 2 nested for loops. And for each cell, here we are at the level of determining for one cell, it has to count the number of living neighbors. So in this box, I'll scroll back up to the box. This is what neighbors are. They are 8 because we're counting not just north, south, east, and west, but also northeast, southeast, northwest, southwest. And you count the neighbors and not the cell itself. So 8 cells, not 9. And you have to count up how many are living. And that's if this is true, if this cell value. And then these are the rules. You know, if the number is between 1 and 4, the output is a true. And then these are the other rules for which it will end up with true, and then else false. Okay, so that's the imperative solution. And in this implementation, I made this wrap around, and I'll leave this up so that you can read it while you're doing the exercise in case this point isn't clear. But you know, you've got a board, and you were talking about neighbors. So what about if you're at the edge of the board? What do? The simplest thing to do is just have it wrap around like an old-style video game. You know, your spaceship goes off the edge here, and it comes off onto the edge of the screen here. That's how the imperative solution works. So you can use that as an example. But really, I chose the initial conditions in a way that you don't care until like the 200th, until the 200th application. So if it's too difficult dealing with the edges, you don't have to. So now you can see what your implementation is doing by repeatedly evaluating this Jupyter cell, and you can see it doing the game of life. And so I think when you're working on this exercise, I'll probably be hearing a lot of, okay, did that work? Just to see how it goes. Okay. And yeah, so the exercise is to do this in array-oriented routines. So no for loops allowed. No for loops over the array. If you have other for loops that are not over the whole grid cell, that's okay. It's always just don't do the for loop over the array. And also don't have implicit for loops like inside map, filter, sum, or things in iter tools. Those would just sneak the Python for loop into it in a hidden way. And one rough way to tell if you're following the rules is that your result will be much faster than the imperative Python. That's a way to know that you're actually doing it. All right, so there are hints. I'm not going to expand them now. If this is easy and you want to keep on going, there's more to do. Didn't I say? There's more to do. Oh yeah. If you think you're really clever, do it with SciPy signal convolve 2D. Okay. So there's an easy and a hard. So go at it. We'll see what time it is now. And we'll do, I think I had like, where are we now? 1:50? Oh, okay. 10 minutes late. So this will end up at, it's right now 2 o'clock. Let's go for 20 minutes on this. So So 2:20, and then we have a 15-minute break. And what I'll do is I'll absorb it in the break. It's okay. I mean, we'll end the break at 2:25. There's 3 breaks, just so you know, or 4. So there'll be enough. Yeah, so I'll see you at 2:25, and we'll be all around, all of us, helpers. And so, yeah. Okay, so I feel bad about interrupting because what I hear sounds like it's really productive. And you can keep, looking at what you're doing, but I'm going to be going over solutions now. So yeah. Okay. Of course there is. Oh, okay. If this happens to you, here's what you do. Start it up again. Here it comes. And if you have let your binder lapse, time to bring it back, just like me. And I'm going to go into the solutions directory, see the answer. Oh, in all of these, if you're wondering about these files, there's an unevaluated version and an evaluated version of each. The evaluated is so you can see it on GitHub without having to start a binder after the fact. So we're going to go with the unevaluated ones. So yeah, so let's look at solutions to this problem. And this is, and if you came across this, there's this little warning message. Don't peek at this unless you've tried to solve it. And actually in all of this, I'm not going to do any kind of policing of, this is really for you. If you decide that it's going to be more fruitful for you to look at the answers, then that's what you do. Generally, it wouldn't be. Generally, it's better to go through it because I will be going through the answers with you. That's scheduled in here. I'm going to spend the next 20 minutes just looking at these solutions. Oh, by the way, actually, I should start with any burning questions before I, sort of give an overview of how you go about thinking about this. Something that came out of the session. Okay, that's all right. All right, so I'm going to look at the solution file. And the first thing it has to do, because it's a separate notebook, we have to build up the infrastructure again. So this makes a new world, and we've got the show function. All right, now let's go with the solutions. Before talking about this first solution, I'm going to introduce a new function because the first way to do this is deus ex machina. And what I mean by that is this, there's a function that just does it for you. After that, I'm going to go into actually, what if you didn't have that function? How would you do it with slices? But let's start with this. And I'm introducing the NumPy roll function. To show what the roll does, see this cartoon eyeball? Okay, this is a, would say 8-bit, but it's actually more like 1-bit eyeball. You can roll with it with axis equals 1 to look to the left. Axis equals 1 going with rolling plus 1 to sort of look to the right. Axis is 0 to look up. What it's doing is it's taking that two-dimensional array and it is moving everything over and wrapping around as necessary. And it wraps all the way around. So if we go up 4, then we look up so much that our eyeball comes up from the bottom. This, it turns out, is just what we need. Because let's say that we have this one-dimensional problem of these zeros and ones. We want to count the number of neighbors that are 1. If we roll this to the left, you see all the values. They've been shifted over, and the zeros has wrapped around. Roll it to the right. Oops, I didn't mean to click twice. Goes the other way. And then we add them. The rolled to the left and the rolled to the right, added together, is the number of neighbors that each one-dimensional cell has. So now extend that to 2 dimensions. You have 8 neighbors, so that's 8 rolls. So here, the number of neighbors starts off as a zeroed array, 2-dimensional array. To do northwest, you roll to one way and roll the other way, so one axis and the other axis. For each of those combinations, the only thing that isn't here is rolling 0, 0, because the center point is not its own neighbor. If you do that, then you'll get the number of neighbors, And then when you have the number of neighbors, one of the hints was, like, once you've got the number of neighbors, then just computing the number of survivors is doing some logical operations. You compute the number of births, and the next cell will be 1 if there's a birth or it's a survivor. So this is applying the rules. And these are the 2 ways that you can come out with 1. And so this would do a step in NumPy. And you can repeatedly evaluate this, see the thing flow forward, just like it did with the Python for loop case. The main difference is that it's much faster. Now, it might seem, oh yeah, so this is 0.2 milliseconds, and the other one is something or other milliseconds, which I don't remember. Now, that feels a little bit cheap if you've been spending this whole time trying to find the right slices, and then, oh, there's a function that just does it. Sometimes there is just a function that does it, and so it's worth looking through the NumPy documentation. Oh, is there a magic function that does exactly what I need to do? That's a good first step. But no, you didn't have to just guess roll. There are other ways to do it. So this first way that I'll do does not take into account the boundaries at all. And that's why it's useful that the problem that I set up doesn't need boundaries to wrap around until you get to some really high number of iterations. So let's look at a one-dimensional array again. What we need to have happen is to take this array, get some left neighbors, get some right neighbors so that we can add them. I showed the example of slicing, where you could take off the first and take off the last, and then that shifts them so that there's the same, so that the numbers line up, but at a shifted. I'll get that picture up again. Come on, picture. It's this picture. This is what we need in order to do a roll that doesn't take into account the boundary conditions. So we can do those shifts, add them together, and get that. And the edges are not going to be right. Put question marks here. We have to make some choice. We could have them be 0. And we can do that by making the left or right neighbors start as 0, and then assign in the shifted. So plus equals, or the equivalent. Copy it and add in. So now the game of life, if we were to do that, these are all of those roll shifts. And these are the slices. So now if we're trying to do this shift and add in 2 dimensions, we use NumPy 2-dimensional slices, the ones that have commas. So again, the 8 cases: northwest, north, northeast, west, east, southwest, south, southeast, of different things to add up, and then all the same logic from that point onward. So really this has been a project about getting the number of neighbors. So there's this step NumPy 2 that does not handle the boundary conditions well. And here what I'll do is I'll zip forward 200 steps and check that it gives the same answer as the first solution up to those 200 steps. This is before that puffer fish kind of thing gets to the edge. And so it's the same result up to that point. But then after that point, here we've gotten this far. We're going to run to the end. And what would actually happen if we got the boundary conditions right is this would get to the left edge and come around on the right edge. But instead, because we've put a new condition on it that the edge is full of zeros, edge kills the cells, the pattern runs into it and goes away. And now we've got something that only repeats. So it's sort of like an end state for this game of life. So that used just slices, and it was considerably faster. It should come out. Yes, considerably faster than the NumPy roll. The NumPy roll, I think, if I remember, it was 200 microseconds, and this is 80 microseconds. And that's because we're not doing the whole problem. NumPy roll is more general. Can you get the edges right anyway? If you went to this trouble of doing slices and also getting the edges, congratulations to you. This is hard. And I'm not going to go through it in detail, but you have to do quite a bit of work to get the edges right with slices. That's why I was not making it a criteria of this exercise to get the edges right. And then it'll run for 1,000 steps, and it'll still always be equal to the full solution. And then getting the edge conditions in right and doing all of that work, it does pay off. It's better than the roll, I believe. Yes, it is. Now, raise your hand. Did anyone try to use the SciPy Convolve method? I'd like to see this. Okay. Okay, cool. But did anyone get it? Solution? Yeah? Yeah. All right, cool. Yes, you can also do this with SciPy Convolve, because this problem of counting neighbors is a convolution. Often with these kinds of problems, they force, this being a different programming paradigm, it forces you to, when I want to say think mathematically, that's not true. You're still thinking mathematically when you're doing things imperatively, but it forces you to think about what other mathematical problems is this like. That's not a thing you have to do with imperative solutions. With these, what other problem is it like? It's actually just like a convolution problem if you choose the kernel appropriately. We want to find out for each of these cells C, how many neighbors it has. This is a convolution with a kernel like this, and if those words are not familiar, then never mind. This is not the way you would go. It's a convolution kernel like this, where you're saying, yes, I want these direct neighbors, no, I don't want the thing itself, and summing over it, because that is the number of neighbors. The number of neighbors is the sum of all of those places where it matched. So there is a way to do it, to use SciPy. You get math cred. Did I not do? Somehow I forgot to do that. Interesting that I forgot that somehow. You get math cred for doing that, but it is not actually faster. Some things in SciPy, in order to be fully general, are not as fast as if you roll it yourself in NumPy. And if you really cared about the speed of this, you would probably be thinking about Numba or JAX. And if you go Numba, then you're probably writing an imperative solution anyway, just in compiled for loops. And if it's JAX, then you think hard about the array-oriented solution, and you can often you actually do win. Its compiler is smart enough to really take advantage of that. In preparing this tutorial, I learned about just how smart JAX's compiler is, and I think if I'm doing this again and following year, I'll have a whole exercise on doing things in JAX. Okay, so any last questions about that before I just went over the solutions to exercise 1? Last questions about that before we go on to completely new topics? Just raise your hand if you have a question. Yeah?
You said for NumPy, it's better to write
It would not. If you're so this is a thing to know about using NumPy. You can use some NumPy array-oriented code in NumPy, and you gain nothing for speed for doing that. It becomes just like doing it outside of NumPy. You only really gain from NumPy if you write for loops, and then LLVM knows how to optimize that. But it's interesting that in JAX you do gain from being array-oriented. And in fact, that's the only way to go. And it's actually kind of hard to fit a solution into JAX, which is why it would make good exercises for next year or something. And then JAX is also immutable, so you can't change anything in place. So it gets even more interesting. Okay, so yeah, let's talk about the next part. And since I have here, I'm going to shut down the kernel associated with this notebook because I found that giving Binder less things to think about it works better. All right. Now, first part was about the wonders of array-oriented programming, and with every paradigm, there are situations in which you want to use it and situations in which you don't want to use it. So now I'll be talking about its disadvantages. And I'm going to evaluate up to the current cell just in case. Just in case there's anything in the beginning that I needed. I don't think there is, but all right. So we start, let's suppose that SciPy doesn't exist and you need to calculate the gamma function. And okay, this is some weird function. It's one of these special functions that mathematicians in the 19th century got excited about, but now it's just one of these things that you find in libraries. SciPy.special.gamma probably. But if it doesn't exist, then we'll have to implement it ourselves. So there's a book for that. Does anyone recognize this book? Just quick hands. Cool. It's still around. Yeah. I use my Pascal version of this to work this out. Let's see. So you find it on page 214. If you want to compute the log of this gamma function, there it is. There's an algorithm. And in that book, they have only scalar solutions because they assume that you're going to be writing in some compiled language. First version of the book came out in Fortran, then they went, Pascal, C. I think this is a C++ version. But they only did compiled languages for this, so it's all imperative. And their solution looked like this. And by the miracle of duck typing, the imperative solution is just like the vectorized solution. So they said, you're going to step through this function, you're going to add, you're going to multiply, you're going to have a loop over these constants. These are coefficients, cof, and you're going to do this thing to each one of them. And just so happens that if instead of x being a scalar, if x were an array, all of those steps would still be valid. Everything would just go right through. So we can write a vectorized array-oriented version of log of gamma. Why didn't that happen? Oh, thank you. Thanks. Do that. Run up to restart kernel, run up to the selected. I should have checked that. Thanks. And it'll eventually get to this. You know what? I'm going to stop it from wherever it is. And it'll be fine to go from here. Sure. I don't have any definitions we need. Okay, that's what the function should look like. And I evaluated on this lin space, this linear space from 0 to 10, 10,000 points. Evaluated at all of them just to see what the shape of that curve is, excluding 0 there. That's the correct shape, as you can see from pulling out SciPy, and yeah, it has an implementation of this same function and they overlap. So we're good. All right, so score 1 for array-oriented programming, which is didn't have to change a thing in that function to get it to work in an array-oriented way. What am I saying about the list comprehension? I gave it okay, so first, yeah, I gave it a list comprehension, so we do it over scalars, and then we're going to run it vectorized. So I got ahead of my own notebook. Yeah. First did it with a Python for loop, and then I did it array-oriented. And of course, it's the same. Yeah, so it automatically worked because every one of these variables could be arrays just as easily as they could be scalars. As long as the shapes match or are broadcastable. All right, now that's one special function. Here's another special function. And on page 219 of the book, here's how you can compute an incomplete gamma. Stepping through this function, and what they say you should do is you should iterate no more than 100 times, recompute this value, and then when some delta gets small enough, then the thing has converged and you can return from your function at that time. And if you get through all those 100 iterations and it hasn't, and delta never got small enough, then you got into some place where this function doesn't converge. That's fine for imperative programming. Over these ranges that we're looking at, it does converge, and you can get, by doing these list comprehensions and passing each value into incomplete gamma p one at a time, you can draw the curves. This is actually a figure from the book. And now if you run the special function, yeah, it's the same. Okay. But this is the crux of what is difficult in array-oriented programming, this iterate until converged thing, or iterate until diverged. But anyway, iteratively apply some solution, some task until a condition is met, and at that point stop. That's a thing that's very hard to express, well, if at all, in array-oriented programming. So let's say that we just take an array xs, plural of x's, and pass that array into the function. It complains. Now let's do another round of hands. Who all has seen the truth value of an array with more than one element is ambiguous? Yeah. So you're NumPy programmers. You've seen this. This will happen like 10 times a day. And it's because here, the result of that comparison and multiplication is an array. If array is a thing that NumPy authors did not want to be misinterpreted, so they just have it fail. And that's actually good, because the bugs you would get if it didn't just fail, it would be doing something would really not be what you intended. Yeah, and so the if statement can't be evaluated in an array-oriented way because we can't have some values of the array enter the if block and other values of the array not enter the if block. And actually, if you get into writing JAX code and trying to JIT compile a JAX function, this is the bane of JAX code too. It's the same problem. It's array-oriented. You can't express if statements this way. You have to do numpy.where or something. So if you have an iterate until converged problem, what do you do? Here's a branch point. Suppose we have all the values continue to iterate, even if they've already converged. Just let it keep computing needlessly. Or keep track of which values can have converged already and keep computing those, but not the other ones. This one is definitely easier because here we just say, do the log of gamma, and here this is the iterate 100 times, and even if even if delta has become a very small number, keep adding it in. not going to hurt that you're adding zeros a whole bunch of times. And it works. And this is a general thing. In array-oriented programs, sometimes you prefer to make the computer do extra work. Now, keep track of which ones have converged and don't compute those. That means that you have to see, okay, make an array of is converged, or sorry, is not converged. And then first, those are all true. And then in this loop, we compute the delta and the summation for the ones that have not converged, and that's a mask. If you've not converged, you need to keep computing those. So put the mask here. The array of booleans inside the brackets is fancy indexing. Put it here on all of the arrays. And then the not converged, you and in. When something has converged, you and it in so that the ones can go to zeros. And then as you keep doing that, you might get to the point where they've all converged, and then these three steps are like, basically just sort of skipping over the whole array each time. And you can do that. It does work. So which one's faster, right? The bottom line. As it turns out, the one that was, in this case, the one that was easier is faster. So keep that in mind. Doing less work and not trying to keep the bookkeeping, you might actually be doing yourself a favor in both the maintainability sense and also the performance sense. Now, in this problem, if this had been iterate 1,000 or 1,000,000 times, then maybe actually bookkeeping would have helped. So it really comes down to a problem-by-problem basis. So, exercise 2. We check where we are. We are still good. Yeah, we're still good. All right. The iterate until converged problem is going to be descending a decision tree. So first of all, decision trees. What I'll do is, again, everybody raise your hand. So all hands go up. And put their hand down if you've heard of a decision tree. Okay. Well, I'll be introducing just enough. And so this is good because we'll be working with them. And actually what mostly matters here is the tree, just walking down a tree. So to make a decision tree, I will just use scikit-learn I'll give it a hardish problem. There's these points to classify. This is they already have colors, and what we're looking, the points have colors, and we need to find a machine that will, given an XY point, to predict whether the dot there is going to be orange or blue. So we ask SciPy to do that, and it makes us, using a decision tree classifier, makes a decision tree. And this is what the decision tree looks like. For every XY point, it will say, yellow or blue. And it has optimized this tree of choices that it needs to make, which I'll show in a moment. It's just a flow chart. It'll optimize that flow chart so that what it's predicting for blue will usually be blue. So, and so actually for what we'll be doing, what's important is not whether or not it's a good fit. Actually, if you're into machine learning, you'll see that this is way overfit. There's points here where it's trying to, it's making decisions based on individual data points. But really, I just wanted a tree. And this will draw the tree. Yeah, this is the tree that we got. This is the tree that made the diagram above. It is a flowchart, and I know at some point I have a diagram of a flowchart, but each one of these nodes is saying, if x is greater than something, if y is less than something, go left or right. And it just goes left or right until it gets to a decision at the leaf of the tree. So that's a tree. In computer science classes, trees are usually introduced as a data structure like this. You have some sort of a class that has, members of, some of its members are the same class, so you just have nodes that have nodes under them. And the decision tree has a method for walking from one of these. So you start at the root of the tree, this node, and then based on some attributes that are attached to the node, like if x is less than 5, go to the left, and if it's not, go to the right. And it just does that. It just recursively walks down this tree. That's what this function is. And here's an example of a tree, just to give an example, small tree. All right, so, and then you can call the predict method at different xy points, and it'll say orange or blue, because it walks down. And that's a flowchart. So, but it was a automatically generated flowchart. That's what that machine learning model is all about. And actually, if I was ever like teaching a machine learning tutorial, I would start with decision trees, because they're just the simplest. You can see all the moving parts, exactly what it does. All right. But this decision tree, because scikit-learn is a professional library, they wanted to make things go fast in this NumPy world, all of the attributes of the tree that they have are actually arrays. It does not have in it the class node that I described. It has just several arrays. And this array is showing all of the nodes of the tree. Some of these values are -2 because this is a node that doesn't have any children. It has, some of these are leaf nodes, some of these are interior nodes. But this is how it stores it internally. It has, an array called children left and an array called children right. Okay, so how this works, how it is you can express a tree using arrays, is that these arrays of integers are indexes of where to go next. So between this children left and children right, the root is the first element. And going left means go from index 0 to index 1. Going right means go from index 0 to index 136. So another cultural reference, you guys, does anybody know about Choose Your Own Adventure books? Has anyone played, with those? And they say go to, because it's a text-based adventure game in a book format. And it says, if you want to open the green door, go to this page. If you want to open the red door, go to that page. And so you flip to that page and keep your finger in the previous one in case you decide you want to go back. This is exactly that. Instead of page numbers, these are index positions. So it represents the whole tree in just a few arrays. Okay, so these are pointers that act as indexes. And how you use pointers in NumPy is put them in square brackets. If you put an index in square brackets, that will take you to that point. So, for instance, if you start at index 0 and repeatedly take the children right array and put that index in there, and whatever it returns is your next index, if you repeatedly evaluate that, that walks down the right. So 0, 136, 138, 148, that is starting here and walking right, 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 and then reaches a leaf. So this is just getting you familiar with what these objects are that you'll be working with. If you want to do this iteration, this thing where you're going to go left, right, left, right, left, right. I just wrote some code to go left, right, left, right, left, right. And that's just walking down that tree in an arbitrary pattern that I chose to show that you can just walk down the tree by repeatedly applying the array. And so array application, like put those integers in square brackets, means tree traversal. Okay, so to check this interpretation, let's write a recursive tree walking function and compare it to scikit-learn's output. And this tree walking function prints the tree. So here's my printed tree and scikit-learn's printed tree, and just scanning down this, you can see that yes, this is how you do it. Just each of these nodes reading whether it's going left or right depending on the x value or the y value, what the threshold is. These are all just arrays that were pulled out of the thing. And so that's the tree in ASCII. So now we can write the predict function using these arrays. If we're at some position, this is an xy point position on the two-dimensional grid. We want to know if that position is orange or blue. Start the array index at 0 and ask, does it have children? If it has children, which feature is it? Is it x or is it y? What's the threshold? Just pulling these things out of arrays. What's the left index and the right index? If the position for feature x or feature y is less than or equal to threshold, we're going to go left, and by go left I mean recurse this function, otherwise recurse right. And if you don't have any children, then you're at the end and you just grab the score. This is going to be just grabbing the score. This is you're given this. This is the imperative function. You'll be writing an array-oriented function to do this thing. To see that it works, we draw that diagram again, the plot of points, and it takes a long time because it is a slow, pure Python function. There we go. Notice the lag? That's because this is a slow version. It is basically, every time you do it, like walking down the tree, one at a time. One call of the function, recursing all the way down to the bottom, is going to find out where one point on this xy plane is. What we want to do is something that looks like this. We've got this prepared data of all the xy points, and we want it to look kind of like you're doing this, sending all of them down, and all the points on the plane, all the xy points, are all traversing the tree together. This is just a mental image. Okay. And this is a quick reminder that you can slice an array by an array of integers. So if you're unfamiliar with this, as soon as the exercise starts, raise your hand and we'll talk. But this is the fancy indexing of integers. So you put a big array of integers inside the square brackets. Okay. Note that the tree has a maximum depth. It's 10. That'll help. And yeah, go at it. Find a solution. There's a suggestion to break it down into two parts. One is a predict, and to walk separately from predicting. And there are hints. So yeah, get started, and raise your hand if you have a question about this point of array indexing. Okay, again, just talk with your neighbors, groups of 2 and 3. And we're going to go, let's see, how did I do? 306. Okay, so it's 340. Anyone, actually, at this point, I'll be going over the solutions now. At this point, does anyone have like a question or a comment that, about this overall? Something I want to shout out or raise a hand or? No? Okay. So I'll start into it and go into the solutions directory again. Number 2, unevaluated. All right, and then first, we'll get back up to the point in this notebook where we're ready to go. Recreate the decision tree, predict single, and then actually making the plot. Remember how slow this was with Python. Again, a few different solutions. And actually, if the solutions look, they look big with lots of stuff in them, it's actually because there are several ways to do this, several valid ways to do this. And I want to touch on them all depending on the different divergent ways that you might have gone about it. So with this, there is a purely immutable way to do it, and then a way that changes the arrays in place. So that's what I mean by immutable. The first solution leaves the arrays as is, the arrays of x and y data, and well, all of the arrays once created are not changed after they're created. That's something that if you are looking into doing some work in JAX, you have to do that. That is the way that JAX works. So let's start with the purely immutable. Not allowed to change an array after making it. Okay, so we start with these positions, and actually let's look at them. I think maybe this. These positions are xy points. This is a set of just 3 of them because a small number of things is good for debugging. We can pass, so to start with the positions the positions are a given set. These are all the xy positions in the plane. Here we're just going to simulate this with just 3 of them. The array indices, we start with all zeros because at first they're all at the root of the tree, and the root is at array index 0. And then what we want to do is want to pass them all through the tree, and then they all become at different indices. And let's do the steps one by one before wrapping it up into a function. So one of the things we'll need to know is at each point in the decision tree, should we be choosing x or should we be choosing y? That's the feature. So we can apply them all to that array by putting the array of indexes 0, 0, 0 into square brackets right after feature. And so now we're finding the feature associated with 0, 0, 0, and it really should be the same number 3 times. What are the thresholds for 0, 0, 0? Well, it's the same number 3 times. The children, if you were to go left, the children, if you were to go right, yeah. As long as we're putting all of the array indices that we put into it are the same, then the array values that come out should be the same. This is actually, there's a very real sense in which an array is a function. It's a function from index that you put in square brackets to the value at that cell. And if you really want to get into it, passing a bunch of indices like this is like function composition, but I'm not going to go there. All right, so so first they're all the same because they're all at the root. If we were to just ad hoc, in order for some testing, decide that the first should go left and the other 2 should go right, what we would be doing is we'd be changing the array indices from being 0, 0, 0 to 1, 136, 136, because left is 1 and right is 136. So let's just ad hoc do that now. And if you pass that into the feature, you get different things for each value. Pass that into thresholds, you get different things, and the lefts and the rights. So we're getting different results for different array indices. Array-wise, the ones that have children are the ones for which children left is greater than or equal to 0, so it has a place to go. This array is set up in a way that there are a lot of different indications that you're at a leaf. One of them is that children left is negative. Also children right is negative, and the feature is different. Most of the arrays give you some kind of indication. We just choose one. The ones that we'll be choosing left are the ones for which when you evaluate the positions for all of them and choose the right features, they are element for element less than the thresholds. Those are all the ones that go left. Okay, so far so good. I see some nodding, so. Okay. So this expression, this actually was the first hint. This is a two-dimensional slice in which we take every member of the first dimension in order. So this is a bit like having a colon here, except we need it to be a fancy index. We take everything along the first dimension. That's why this is an A range. And we'll either take feature 0 or feature 1 of the second dimension. The second dimension is the x and y's of our input data. There's a way to do this in smaller steps. I'll try to do that. I think that that would probably be a good idea. So if these are the input data, these positions, 0.1, 1.1, 0.2, 2.2, 0.3, 3.3. The A range is just counting numbers. Let's say the features are x, y, x, y, x, y, 0, 1, 0, 1, 0, 1. Here I want to point, so I'll take this with me. Where are we? Where's the output of that? My output cell. Oh, I didn't evaluate it yet. Oh, I see. This is what is the output? This is the output. This is the output. Okay. So in each of these, we're taking, we're just walking through each one of these pairs. 0.1, 1.1, 0.2, 2.2. We're taking from the first dimension. We take each one of these. We'll take one of the pairs in each step, and depending on whether the second dimension is 0 or 1, we'll take either the left of the pair or the right of the pair. And so that's why the output is 0.1, 2.2, 0.3, 4.4, 0.5. So making these little test cases can help you design the slices that you want to make. And really, it's perfectly good that to be putting that much thought into a one-liner. This is fine. If you are used to imperative programming, you would just would normally be trying to blaze through all of this, but this is really more. This is concentrated code. I see, and then these cells are another way to do it. Take a bunch of trues in the first dimension. True, 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 true. We're going to take every pair And from each pair, we'll either take the left or the right. So there are different ways of setting up this slice. This was the hint 1, by the way. So now we know which indices we'll be choosing left. We need an updated array indices to select, to know whether to be selecting from the left indices or the right indices. So here, let's say that we have this choosing left, true, false, true, false, true, false. So like, again, I'm making synthetic examples that are easy to see in the output, what the slice did. So if I have these left indices and these right indices, which I've deliberately made very easy to read and different from each other, the NumPy where function will take trues and falses here, and based on whether it's true or false, either pick the left or pick the right. And this is the immutable solution because it leaves the original array indices array as it was, and it makes a new array. And np.where is good for that. So actually, if you're doing JAX programming, you'll be doing a lot of np wheres instead of if statements. You'll be turning all your if statements into NumPy where. We're not done because some of the nodes don't have children. This is the iterate until converged problem. You know, on all of these data points going into the tree, some of them will have reached parts of the tree that don't have any children. So we have to do something different with them. We can't send them to the negative indices, the negative numbers that mean you're at a leaf. So we want something where we can keep computing something for them, but not have them go anywhere because they're already where they want to be. We want to compute, should I go left or should I go right? And the answer to that is, yes, you should stay right here, right? We want to construct code that would do that for them. So if they have children, something we can determine by seeing if left is negative, we can put the NumPy where that we just wrote inside a NumPy.where. If it has children, go to left or right child. If it doesn't, stay where you are. Assign x, you know, the next x is going to be x. This could have been 2 lines, actually. You could have taken this NumPy, this inner NumPy where, which again, I'm assuming, oh, you can see the selection. You can see the selection, that's good. The inner NumPy where that is selected, you could have put that in a temporary variable. That would all be the same. So putting all these pieces together, here is a function that doesn't traverse the tree. It predicts the next step down the tree. You're at some node, and this function will tell you all of your inputs are all at different nodes at one depth. And this function will predict where all those nodes are going to be at the next depth. And does all the things, it just wraps up in a function, all the things I just talked about. Applying it to some synthetic example, small 3-element thing. This one predicts they should all go left and keep hitting it, and they all walk until, look, more iterations are not changing it. They're all doing that x goes to x thing. So I'll do it again just for, you start off like that. They all want to go, one is maybe, yeah, one is to the left. And then they all go in different places down the tree until, some of them reach leaves before others, but eventually they all reach leaves. So we want a function that iteratively applies this predict many step. How many times? We don't have to do it more than the depth of the tree, because then, you know, when you get to 10, everything is converged because there's no more tree left. So predict many wraps all this up. Makes initial array indices that are zeros, iteratively applies this predict next step, and then at the end of that, it does the same leaf decisions that the pure Python did. Because when you've gotten to leaves, then you just have to read off what the decisions are, and so that's the same code. So in one step, that goes to the solution. And now we can make a plot with this predict many. And that plot appeared a lot faster than the Python plot. In the things that you were working on, how many people were trying to write something that did not change the array in place? A few? Okay. How many people were working on something that did change the array in place? Okay. That doesn't add up to everybody. And really, I can't think of any other possibilities. But okay. So there is a solution for doing the many in place. Oops. Here it has a lot of the same pieces, but instead of the where clause, they would say an array of booleans of whether you're going left or right, and then moving left as the second argument and moving right as the third argument. Instead of that NumPy where, you can just take your indices and actually change some of them. Select out the ones that we'll be choosing left and set them to choosing left. That doesn't look very different. You know, it's really just that NumPy where. The rest of this is all the indexing to get to this part. And then it works the same way. And we can make the same plot. So from here, the rest of this solutions is interested in performance comparisons because, you know, do things in place. They're often a bit faster. Question is how interested. And then also it also goes into doing this imperatively with Numba. How does it compare to that? Doing with JAX. That is, I think what I'll do is I'll not get deep into the details. I'm just going to run them all. And then while they're running, we get bottom line results. Let that all go. And just talk about the different ways of doing this, and then we'll see for this particular problem what the results are. And in fact, the single tree at a time Python function that is so slow, I'm just going to stop it and have it only go for one. Run them all like that. Okay, so we have the original Python iterative solution. We have NumPy changing things in place, NumPy not changing things in place. Other possibilities, we can do the single tree traversal. You might say, okay, well, the NumPy was fast because it's doing this in compiled for loops. What if we take Numba and do the imperative walk down a tree? And because Numba will compile this would be like if we wrote this function in C. And it also has the advantage over NumPy that it's not making intermediate arrays. What we'll see actually at the end of this is that is in fact slower. This is a case where even doing something imperative compiled, like it's a C program, this recursive walk individually for each data input is slower than walking all of the inputs through the tree at the same time. So here's something where array-oriented programming is really, really paying off for performance as well as for conciseness. And there's an array-oriented traversal, which we can compile because we can take our array-oriented solution as an array-oriented solution, not turning it into for loops, and compile it with JAX, which, yep, it's the same two functions, just doing a jax.jit. And now this, we let JAX know, we're giving JAX more information about this, about the fact that they're array-oriented. By not writing out the for loop and saying you must do this step before that step, we give the compiler more freedom to make optimizations. And it turns out that that is very fast. So the final results, drum roll. In a log scale plot, the pure Python course is always going to be on the far end. Recursively walking each tree in compiled NumPy. So this here, this first bar difference, that jump of well over a factor of 10 is going from uncompiled code to compiled code. Yeah, we expect there to be a big jump from that. But then going from even this compiled iterative solution to where it's taking, the single plinko, the single thing going down the tree, and then another point going down the tree, and then another point going down the tree. If you just change that to having all of the points going down the tree all at the same time, we get another big speed up. Bigger, in fact, than the difference between immutably replacing arrays versus changing the arrays in place. So changing the arrays in place doesn't actually buy us a whole lot here. Sometimes it does. Compiling that in JAX is able to take that array-oriented solution and make it even a little bit, trim it down a little bit more by compiling all of the operations into a single pass. And then scikit-learn's implementation is faster than that because they spent a lot of time optimizing that. Actually, if I run this on a different machine from Binder, the JAX is pretty close to the scikit-learn. It depends on what hardware you run this on.
What are the optimizations like is it NumPy or is it something compiled?
Well, given it's compiled, it goes into C code. But given this difference between this compiled iterative NumPy with a recursion versus not recursing but doing it array-oriented through, I think that their implementation is on arrays. After all, they represented the thing as arrays. So.
But NumPy is not actually in the fastest C, right? You made it sound like that.
Oh, that is, it often is.
It often is like.
Yes, often NumPy is as fast as C. Actually, the very next thing. Yes, very next thing I'll be going into that. Yeah. So yeah, that's among the tools at your disposal. NumPy is it compiles a subset of Python to something that runs as fast as C, and then the key part of that, it is a subset of Python. It has to strongly type, just like C strongly types. 404. Yeah. All right. So I'll talk about that here on run this one on Google Colab. And you can do this too if you have a Google Colab account. Because this one takes another iterate until converged problem and runs it on all the accelerators. So we're going to use NumPy, we're going to use JAX, there's array-oriented solution, there's imperative solution, CPU, GPU, that's the reason for Google Colab, because you can run things on a GPU. And I have decided, just a moment ago that I will just show this to you, but I'm not going to run it. It has the final results at the end. But here it's on a platform that can run GPUs, so you could do it. Mandelbrot. It's not like walking down a tree. It's the thing that makes these plots. Okay, it's the thing that makes these pictures that were, calendars and such. And it does that by, this is a complex plane. The horizontal axis is the real axis. The vertical axis is imaginary. And if imaginary numbers, complex plane, if that's, it's some calculation. That'll be enough. And for each one of those points on the plane, z, it applies the function z gets replaced by z squared plus c. And c that's the point where it is on the complex plane. At first, z is equal to c, and then you iteratively apply this. And in doing that, some of these points, the values diverge, and some of the points, they don't diverge. That's the difference between the yellow and the blue. When they diverge, the iteration number at which they diverge is what we color this. So if they diverge right away, it's deep blue. If it takes 2 steps, it's this. If it takes 3 steps, it's that. That's why actually you can see lines here, because it's an integer number of steps before it diverges. So that's the algorithm. This is how you compute it in Python. Double for loop over all of the pixels, and then for each pixel, you just keep applying that, at least 20 times. And if the absolute value of it seems like it's going away, like it gets bigger than 2, then you call it divergent, and you say at that point, this is what color we're going to make it, and you get out of that loop onto the next pixel. That's very imperative, because you only iterate until you see, oh, this is clearly diverging. Then you move on to the next pixel. That's the thing that's hard to do in array-oriented programming. And you can make that picture. This picture is low resolution and slow. All the other pictures will be high resolution and fast, because this is done in pure Python. So we don't want to do as many pixels. It just takes too long. Okay. We'll see a summary of all those numbers at the end. The array-oriented solution, now we have this problem again of like what happens when we get to a leaf of a tree? What happens when we need, what was it, the Bessel function or whatever that special function was, to see if some computations converged. Here we want to know when does this pixel diverge? And you have to keep track of which ones have diverged, and only apply the calculation to those. Actually, if you keep applying it and let it diverge very, very far, it gets to infinity and then nan. So we want to clamp this. So this is the reason why we wanted to do some bookkeeping. So it has to be rearranged to do that, but then you can make the same plot. Now we go to town with every possible way of doing this. Suppose that we write it out as a C++ function. Compile that as a Python module and run it and make the plot. So now we do the imperative solution in C++. You can see why I didn't want to just evaluate this. I think we should just skim through. Python instead of PyBind 11. Okay, well, this is again C++. NumPy. Here we get to write our original Python for loops, but it is as fast as any compiled solution. So it's answering your question. If you do something in here that you cannot compile, you get a lot of error messages from NumPy. That's the price. NumPy vectorize, just a different way of using NumPy. CuPy. Okay, CuPy is a library that has the same interface as NumPy, but all of the arrays live on a GPU. So GPUs are especially good for vectorized solutions, which array-oriented is vectorized. And here, yes, here I'm addressing the thing in the chat on Slack. I use the word array-oriented when we're talking about just a programming style, and the word vectorized for the hardware speed up that this programming style can take advantage of. And people who work in hardware vectorization bristle if you if you don't use the word that way. So we just take our NumPy solution, put it on CuPy, and now it runs on a GPU. So a GPU made this plot. CuPy with a custom kernel. So now at each pixel, we write an imperative solution in C++, actually CUDA. Numba has a CUDA backend. You can write Python, run it on a GPU. I hope this isn't getting monotonous. We'll get to the plot at the end. And then JAX, you take the array-oriented solution and you flip a switch. You say, run this on a CPU, run this on a GPU. And the final results. These results were run on like a significant computer, not on Google Colab. If I reevaluated this thing, the bars would move a little bit, but not enormously. There's Python. You get some orders of magnitude speed up from just using NumPy. Oh, by the way, why are we looking at this plot? This gives you sort of a sense in the back of your mind. What should I be reaching for? Like, sometimes you'll hear people say, oh, NumPy is fast because it's much faster than Python. Sometimes you'll hear people say NumPy is slow because it's so much slower due to the intermediate arrays. It's because, well, on a log plot, it's between those two. So go from pure Python to this array-oriented NumPy. You can gain a lot. And then just compile the loop in pure C++ with PyBind 11, the C++ Python hybrid that is Cython, Numba, a compiled subset of Python, Numba vectorized, just a different way of using it. All of these are all pretty much the same because they were really doing the same thing. They were doing this imperative solution that I wrote out and then just written in different languages, but they all compiled to the same machine code. That's why they're all at the same level. JAX on a CPU is a bit faster, and I never quite found out where they're getting that extra bit of speed. Actually, it was quite a lot of performance tuning to try to figure out how to get to the level where JAX just was right away. And this was the day that I became excited about JAX. CuPy, just putting it on a GPU, is like the difference of going from this NumPy solution, because it is the same code as this NumPy solution just on a GPU. It's from there to there. And it's just taking it from a CPU and putting it on a GPU. And then you're making these intermediate arrays, which is a problem. So you write a custom kernel in CuPy and you gain a lot. Writing NumbaCUDA is writing a customized kernel. And then the thing that you get out of the box with JAX is just that. You just put the same code you would write in NumPy into JAX, and you're there. So this kind of this helped inform my mental map of how all these different accelerators can help, and I hope that this is useful for you too, because this is how we should be thinking about these things. The speed up versus effort. Some of these things are easy, some of these things are hard. I can tell you that Cython was especially hard. It was very hard to get to this point with Cython. And then you can look into that in more detail if you want. This link exists. Okay. I think now. Oops. Yeah. Well, of course. Go back. Now we're on to beginning of exercise 3. Perfect. Wow, my timing is so good. Didn't think it would just work out like that. Okay. I do have to restart Jupyter, though. Finder, I mean. Okay. Any questions about that while this is oh, any questions anyway? Right. Well, some of those in that bar chart, some of them were all the same CPU and some of them were all the same GPU. So actually, so there's only two. There were only two hardwares on that plot. It's the single pass thing. Yes, the thing that just applying CuPy, just taking the plain NumPy code and turning all the NP to CP, turning NumPy to CuPy, that first speed up was just the fact that you went from CPU to GPU. But then it was making all those intermediate arrays that are, you know, the problem for when you really want to optimize, when you really want to get fast. CuPy was making these large intermediate arrays and wasn't able to fuse those operations, meaning, you know, you've got several steps in your mathematical function and you want to do all those steps before moving on to the next, right? That would be the most efficient way to walk through it. Writing the custom kernel applied all those steps before moving on to the next pixel. Yeah, and then Jack's compiler did that. And that's why Jack's got there without having to write a custom kernel. And that's very specifically what JAX is for. It was the purpose of it is for fusing. The reason that JAX has a JIT compiler is for fusing operations. That's the stated reason for being. Okay. Now we're on to weird arrays. This last section will be, actually, I don't think I need to do that. I think I just need to import NumPy. Okay, up till now, all of the arrays that we've been dealing with have been rectangular. In fact, all the arrays that people usually ever call arrays are rectangular. You know, they'll be, maybe you call them tensors if they have a lot of many dimensions, but they are rectangles in all of those dimensions. Now we're going to be looking at some arrays that aren't rectangles in all dimensions. So other data structures. What if we had variable length lists? What if this was our array? You know, here we have some element, some record-like thing that has two fields, x and y. The x field has a number in it. The y field has a list. And there's a variable number of these. The first array element has 3 of them. The second has none. And the third has 2. You know, what if you have data like that? And I've written the data like JSON because what we normally do when we have data like this is we, you know, express it as JSON. It's the most handy format for doing that, especially cross-language. But JSON is text, is ASCII text. We want something binary so that we can run machine code on it immediately and without deserializing. We want these to not be objects like Python objects, you know, a variable type. We want something of some fixed type so we'll be able to run compiled operations on it quickly. So there are solutions for that now. This all is very recent. We're talking about, you know, pretty much, actually, absolutely everything that I'm talking about here. I don't think there, no. With lots of extensive searching did not exist. You know, there was nothing like this before before Arrow. So let's see this. Let's take this array and load it as a PyArrow array. Arrow is a project that has many different language backends, but Python is one of them. It presents the data in a rather complicated looking way. But you can convert that back into a Python list and see that the list is there inside this object that has child types and is valid, all not null, and all that. So this is kind of a PyArrow is designed. Arrow actually is designed as a low-level library used by other things. It's an infrastructure. And we can do some NumPy-like operations on it. Suppose that we take this array and slice off the first entry. And then we'll turn that into a list so that something we can look at. Now, before we had 3 records in the first, 0 in the second, and 2 in the last. Now we have 0 records here and 2 records here. We've sliced off the first one using this NumPy-like syntax. Or if you want to do an array slice, put an array in square brackets and pick arbitrarily from these things. It's not with the square bracket syntax, there's a take function, but you can do that. So here's the first list that has 3 records in it, and then the third list that has 2 records in it, and the one with 0 records is not here anymore. Internally, the data structure is a collection of densely packed buffers. So you can ask what they look like, but it's not really going to tell you. It's going to say, yeah, some of these places where there ought to be buffers, there are buffers, and others there don't need to be. We can examine each one of these buffers by turning it into a NumPy array and see that the data are in it, and the data are concatenated. So these values, 1.1, 2.2, 3.3, 4.4, all belong to the X field of different records. But the way it stores it internally is it puts them all together. So it makes it array-like, this data that didn't look array-like. And some of these are integer arrays in order to make that structure like the variable length lists. The primary focus of the Arrow project is to share memory between languages and between applications, so that all these different applications, Spark, Pandas, Drill, Impala, all Parquet file format, you wouldn't have to convert between each of these n and the other n-1 of them. You would have one in-memory representation that they can all talk to. And they wanted this common representation to be something that allows for fast, meaning vectorized CPU and GPU, CPU cache-friendly and GPU-friendly algorithms. So these are all taken from their website, all these images. However, it's not really a direct user interface. From what you saw, it's showing these. It's really a low-level thing. So Awkward Array is a library for looking at that sort of data in a data analysis. It presents a generalization of the NumPy functions. So whereas you might do a slice in NumPy that would, cut things a certain way, if you do that same slice on an awkward array, it has it does the irregular version of that slice. So I'll be showing examples from a version 2 that's right. And I'll restart this and be talking about it while. This is a library that is in production. And many of the users are all on version 1. But we are, and I'm involved. I'm the project lead for this, and so wanted to find a way to to say that. And we've developed a complete version 2, but it's not going to take the place until people are ready to transition. So, and I'm only going to show new stuff here. I'm going to do that. So version 2 is a submodule within version 1. So that's why I'm importing it in a strange way. Get here, there, and that should get us back. Okay, so pull the awkward array from arrow, and the representation is not deep internals, but showing a little bit of the data. But this data could be very large and structured, so it's a compact form, but you can expand it out. And the data type becomes a very interesting thing. Normally arrays have a shape and a D type. A shape for what kind of rectangle is it and how many dimensions. And the D type is what kind of data. Are they floating point? Are they integers? Are they Booleans? Now with this more generalized kind of arrays, the data type becomes a bit more complex. It's an array of 3 variable length lists that could be missing or not missing, could be null or not null. And they have an X field that could be missing or a floating point, and a Y field that could be missing or a list of possibly missing integers. A lot of the missing types come from arrow, where everything is potentially missing. And just as with arrow, you can peek at the internals. How is it laid out in memory? Here we can see that the 1.1, 2.2, 3.3, 4.4, 5.5 is all contiguous. And so when we run NumPy-like functions on them, we can run compiled functions on these contiguous buffers. But then all of this stuff is orchestrated in Python, so it can give you a view of it that looks like plain old data. Okay, so the use of this is like NumPy, but for data structures. So say we have an awkward array, it's that one, and then we slice the X fields out. So just like slicing, but now we're going to slice a field instead of some values. So these are all the X's. We could have sliced the Y's, which had lists within lists. So there's a generalization of slicing, although NumPy has structured arrays that slice like these also. So in every case, when NumPy can do the same sort of thing, we have exactly the same syntax. Slicing multiple dimensions at once, like the field, and also, a fancy index of, slicing with a Boolean to take this one, don't take that one, take this other one. And then doing some mathematical operation like a square root just across everything. It's ufunc-like. Sorry about the figure. Reductions get interesting because now if you are reducing along this dimension, some values might not exist in some of your lists. So we had to define out what it means to reduce along variable length lists. But the definition makes sense. We can take this and slice them this way. 1.1 plus 4.4, 2.2 plus 5.5, which is 3.3. Or the other way. 1.1 plus 2.2 plus 3.3 is 6.6. There's nothing in there, so it's 0. 4.4 plus 5.5. Slicing the Y. And then this has a third dimension to reduce over. So some fields can reduce over more fields than other fields. Broadcasting will be used extensively in exercise, so I want to bring it up here. Say just like NumPy broadcasting, if you have a scalar 100 plus everything in this triply nested list, it will add 100 to everything in the triply nested list. Broadcasting just like NumPy. Here's a question. Or X is 2 levels of nesting, Y is 3 levels of nesting. So that extra level of nesting has to get spread out each individually. And actually, when you start using these in data analysis, it fits together, makes sense. And then you get into operations that you just wouldn't even have in NumPy, like finding various combinations of these. And that's how this is being applied, is for combinatorics, where you have different numbers of things at different places. I won't get into that. Yeah, we won't be needing these for the exercise. Okay, so as a comparison with pure Python, you can have this kind of data in pure Python. But if you wanted to do an operation like this, slice the array, and then at the innermost index, slice off the first element of every one of those lists. Doing that in Python is a lot more verbose. It's for loops and for loops, just like with NumPy. And it scales better to big lists because it's using compiled routines. So now I have, what is this, 100,000? This is the whole memory layout. Just like before, this memory layout looks about as big as the one before, and the bigness is actually in the ... of that array. So we have the same number of arrays, the same number of buffers, they're just larger. So so because of that, it's, oops. The implementations can be precompiled and fast. Next is the exercise. Maybe I'll wait for this, yeah. Doing this over the Python lists a second, doing this over the awkward arrays 30 milliseconds. So it's just like the NumPy speedup. Okay, that's the end of the main narrative, and we'll go to the exercise. This exercise is exploring a data set. So the previous exercises have been really about programming, and this one is about data analysis. Suppose that you're given some data that is awkward. You're given some data that has a difficult to reconcile structure. Geographical data has this quite a lot. Path lengths all have different length. Every path has a different length. So this will be an exercise in analyzing some data from a collection of taxi trips. And it is a big data set. It's all the taxi trips in Chicago over a 3-year period. Actually, the last 3 years. So actually, that is interesting as well. But we're not studying the volume change over the past 2 years. And the data have 3 levels of nesting. There are taxis. Each of the taxis takes a different number of trips. Within each of those trips, each of them has a different length path. Some of these trips, they go around, some complicated route, and that takes a lot of points to describe, and some of them are really short. So we can read the data set from a Parquet file, and Parquet files are especially good for this kind of thing. So this is like JSON structured data, but it's a binary, and it's columnar. And being columnar, we can pull out just some of the data. So here I read I think this is about 1/100th of the data, the first 100 taxis. No, the first 100th of taxis, the first 1% of taxis. But for all of the fields in all of the records. And generally in a data analysis, you're not going to need all the fields. You know, there's some things that in this has payment, the different, how much the trip cost, and the analysis won't be overpayment. So we can, from a Parquet file, not read that part of the data. That's an option we wouldn't have if it were JSON. If it were JSON, you have to read it all. So these are the columns in it, and they have different lengths because, you know, some of them are paths. And they are called columns. We can look at, we can start by looking at the type of the data. This is more complex than the one we saw before. These taxis, each taxi has a variable number of trips. Each trip has, it took some time, some number of seconds, went over some distance, kilometers. It had a beginning and ending, latitude, longitude, and time. Had a path, which is a nested list of latitude, longitude points along it. And what we'll be seeing is that for brevity, for file size, the latitude, longitude points are differences with respect to the starting point. So start at 0 and then increase, and then you can make them lower resolution. And then the payment stuff that we don't care about. I believe that we could just jump to I think that it's self-explanatory to say that we can pick out some columns, you know, say we just want this, that, and the other, and only read those. And the type of this is now simpler because we read less. So this is just to start with a demonstration of what you gain when you have this columnar data. And it's not JSON. You know, we can read just the fields that we're interested in. That's this point here. That's possible to, oh yeah. What is the total list of columns before you read anything? Yeah, that's there for if you want to be fiddling around with this later. Okay, so now let's start. We've read in the data. Let's explore the data. Because this is going to be a data analysis. You start with just exploring, just see what's there. So let's take taxi number 75, and what is all the information about it? And this to-list, we're showing it as Python lists. So I first selected something that's small, so we're not going to kill the browser with lots and lots of output, lots of Python output. Just pick one taxi, and what is all of the information about it? Well, there are multiple trip records. They have fields, and inside of that, the fields have fields. There's nested records all the way down to latitude and longitude, and here's a path. This path is very short. This path is even shorter. Look at that. I deliberately picked a small one. Oh, here's a big path. Here's one of its paths. And it's the fact that these can all differ from each other, which is the motivation for all of this. Okay. So yeah, the second to last of these has an interesting route. So we can select the 75th taxi, the second to last trip. This just, NumPy slices are like this. And look at just that one. And we can extract the numerical data by picking off the field names. These are just the longitude differences, and these are just the latitude differences. And now we've got really numerical arrays. And when we have numerical arrays, we can, you know, perform computations on this. add them, take square roots, that sort of thing. So let's plot this one path. So just using matplotlib to draw it, and that's where the taxi went. It's following the streets. And Chicago's a grid. Now this path starts at 0, 0, because these are latitude and longitude differences. So now what I'm going to do is plot not just one trip, but a lot of them. Because remember the thing I said at the beginning is the value of array-oriented programming is you get to ask a question about a whole data set, about a lot of things, and get the answer back for a lot of things. So now for one taxi, I want to see all of your trips. Okay. And here I'm unabashedly using a Python for loop because I've already limited the size of the data to only that which, there's only like 100 things here. Matplotlib can draw 100 things. If it was drawing the whole data set, the whole file, that'd be millions and it would crash. Thing to notice about this is that some of these look the same, but there's a sort of offset. It's because there's a road there, actually. I think this is the road that goes to the airport. And it's starting at different places because these are latitude and longitude differences. So we want to find the actual latitude and longitude. And here's where we're going to use broadcasting. Because each of these trips, so what we want to do is for each one of these paths, each of these paths has a single latitude and longitude start. We want to take that latitude, longitude start and add it to all the points along the path. And then a different path has a different latitude, longitude start. I'm going to add over that. And you're thinking NumPy, think in the way you would do this sort of thing in NumPy, if this were regular, this would be broadcasting. Like you would have a one-dimensional array of latitude, longitude starts, and a two-dimensional array of difference paths. And you would want to take those starts, different start for each row, and add it to the whole path. And all we have here is that the paths have different lengths from each other. That's the only difference from NumPy. Here, let's go through it like in Python code, just one thing at a time. We have this synthetic example of 0.1, 0.2, 0.3, 0.4, 0.5, and we say we want a begin position of 10. Here's broadcasting. You take the begin position and you add it to all of those differences, and you can get something like 10.1, 10.2, 10.3, 10.4. So to do that to a single trip, here's the begin position. Taxi 75, the second to last trip, and get its begin longitude. Taxi 75, the second to last trip, get all of its longitude differences. And just looking at them, a single begin position and an array of positions along the path. And the broadcasted is we just add them. Often when people are starting into this and they're thinking about it, they ask, what do I need to do in order to, and then they describe some situation. And the situation they're describing is broadcasting, so you just say plus. It's often, the syntax belies. It looks simpler than the thing that you're thinking of. Especially if you're starting from an imperative point of view. So now a lot of trips. Now I'm picking just one taxi, but all the trips. So there is an array of begin positions, and they're different from each other. And there is an array of lists of paths. So it's just one level deeper. So the syntax is just take the many begin positions and the many differences and just say plus. And that adds the right one to each. because they line up. And again, it's just like NumPy, but the paths have different lengths from each other. Now let's look at this in more detail. Some of them are short and some of them are long, but they all have that minus 87, which is, approximately the longitude of Chicago. They're all pretty close to that. And the data type of this that we just looked at is 500 lists of float 64. And some of them could, in principle, be missing. So that's what option means. Oh, I should help here. Option or question mark. They both mean could be missing. Okay, so now I'm just sort of building this up. All the longitudes, all the longitude differences, all the latitudes, all latitude differences. So we add them. And we get rid of the missing values. Is none. There are functions in NumPy for asking questions across an array. This is one that's asking, is the data missing? And so and tilde is not. That's when you're doing logical operations with arrays, tilde is not missing. So there they are. And now we can plot these from where they are. So now these are paths that the taxis took, all in real coordinates. So now it's not a spider all coming out of 0, 0. It's something that kind of looks like Chicago. None of them go too far to the east because there's a lake there. And oh, this is the airport, whether keep going there. Okay. So then, if we want to do this to all taxis at once, this is the broadcasting thing and the way that you think in array-oriented programming. We just did this not with a scalar, but with something that is one level of vector less than the whole thing. So it's the same syntax. So to go from one taxi to all the taxis, we remove the brackets 1. So that's all of them. So we've just corrected we've turned all of the relative paths all into absolute paths with these lines. It's plus. And here's the data type. It's one level deeper than the previous data type. One more var. All right, I'm going to check time. 4:48. This is okay. I think you'd rather have more introduction than time on the exercises. The solution to the exercise is actually a one-liner. So this is maybe seems like a lot of buildup for something anticlimactic, but I think you want to have the introduction because this is new stuff, literally new. So what we'll be doing actually to motivate where are we going with these calculations that start off just sort of exploratory, where we'll eventually be going is we've got all these paths, and the goal of the exercise will be to find the length of each path. Just computing distance formula on the variable length paths. And in order to do that, they can't be in latitude and longitude. They have to be in a distance unit. So convert the latitude and longitude into kilometers. Kilometers relative to some place in the middle. And here I'm doing it approximately by putting a single latitude to kilometers, longitude to kilometers. This is valid on the globe. This is valid in a short, we're only looking at a single city, so it's this approximation is close enough. So here we've turned the latitudes and longitudes into kilometers east and kilometers north. Now those are our coordinates. And then just in the distance units, we'll look at this taxi again. The same trip is making. All that's different now is the axes. These are no longer latitude and longitude. They are distances relative to an arbitrary point, which is, I think, the mean. So that's where 0, 0 is. Okay, the exercise. So long time getting here, but yes. The goal is to calculate the length of a path. And I'm going to give you, give you all the formulas. You got a path that is defined in terms of points in the kilometers east, kilometers north. So those are the XY coordinates. The length of a straight section of this path is square root of delta x squared plus delta y squared. Actually, I want to know how much to belabor this. Is there anyone? No. How do I notice this? Everyone, hands up again. This is the first time I've used this technique, and I'm liking it. Put your hand down if you are familiar with the distance formula in doing this. And okay, I thought so. I just didn't want to assume. So yes, this is the distance formula, and you can calculate like that over one segment, and then the length of the whole thing is the sum of all the segments. Now the complications that come here are, first, you're given the xy positions of these points. You want xy differences. Think about previous exercises and how you did that there. Another complication is that this here we want to sum over something, but we don't know its length, and each one will have a different length. That's what's new. We can do it with an imperative for loop. So example east, example north, I'm just picking one path, 75 minus 2 again, our favorite. There's that array. And here's the imperative formula. And yes, delta x is a variable name. I'm using Unicode. So for I in the range, length of the list minus 1. Because you're doing differences, you can't go over the whole length. You have to be looking at the length minus 1 for all the gaps in between. The next one minus the current one. The next one minus the current one. And now we've got delta x and delta y. So we can compute delta r. And the total length will be the sum of those. Your solution must apply to all trips of all taxis in the data set. And so the output type will be the number of taxis, variable length, and it will have variable length of floating point numbers. Question mark or option, this is missing data. And for this problem, that's just a nuisance. There are missing values, but they won't matter. The calculations go right through the missing values. With your results, if you call distances.show, it'll look like this. So you'll have a way to check that your result is right. And then there are hints. And then I've got bonus exercises if you've got lots of time. And we can go on from there, but let me just say this and give you a lot of time to be working on this. And if you are, really excited and you go on, or actually if you want me to explain the later parts, just call me over. And also with all of this, please do call me over. Any problems? I was expecting to be going around. Actually, I was expecting my 2 helpers and me to all 3 helpers and me to all be going around answering questions. So please do. Please do ask. And that's it. Let's go. The next time is At 5:10, it says I'll be going over. That's 10 minutes from now. No, I won't give you 10 minutes. I'll give you 20 minutes, and then we'll spend 10 minutes talking about the solutions. So this will be 5:20.
I have a general question.
Yeah.
When you're storing things in an awkward array with the metadata, besides the, I guess, pandas overhead, is there an advantage to not storing that to something that would you call like a tidy data set, where you have one row for every single trip, and then every feature of that trip in columns? Is there an advantage to storing it?
Right, that's the last one, actually. That's,
The last exercise?
Yeah, when I said there's these extra exercises at the end.
Okay.
Yeah, there's a comparison to that.
Okay.
Sometimes yes, sometimes no. I mean, there's always, depends on what kind of problem you're doing. But the thing is that trying to fit all problems into tidy data. Okay. Right, so I'll be showing how to do this. Oh, that's why it's so blurry. And the first steps will be getting back to where we were in this new notebook. Have to load the data again. Get all the latitudes and longitudes into kilometers. Okay. And the single path example for comparison, because again, comparisons is good. As a way of checking what we're doing. All right, so start with the one-line solution. One-line solution for doing the whole thing is this line. I'm going to break it down. No, I didn't. Can you believe that? I will verbally break it down. Okay. The image that we want to have, I wonder if I can get to the picture. You remember the picture of the spirally path and then a segment on it, and delta x squared plus delta y squared square root is delta r. And also, I should find my pictures directory, so you can keep working while I'm finding the pictures I want to show you. Shifted operation. Yeah, that's one of the pictures I want to show you. Length by segment. That's the other. Oh, good. I found them. So we want to do this thing. And we can get delta x and delta y using this same technique that we did early on, where if you have some list, some array, and you take off the first one, and then you have the same array with you take off the last one, now they line up, offset by 1. You can subtract in that direction, and you get the difference between each element and its neighbor. And that's how you can get delta x and delta y. And the syntax for this, now I wish I had like a whiteboard. I do have a whiteboard. Look at that. Syntax for this is, with normal arrays, is bigger than this to be seen. Path, if it was a one-dimensional array, it would be, first you take off the first one, so this is all the ladder, minus, take off the last one. So that's what we did in the first exercise. That is here. For the kilometers east, there it is. Can you see the highlighting? You can't see the highlighting. Yeah. It goes from this line, that line. the 1 colon and up to the colon minus 1. And then what these are is the first 2 dimensions. The taxi dimension, the trip dimension, and this is the path dimension. So if this had been completely rectangular, that's exactly how you would do it with a NumPy array. You want to do it on the 3rd dimension. But these are not rectangular. These are all of them have different lengths. They're just lengths that happen to line up perfectly because they come from the same arrays. And because of that, this same syntax just works. So you can think about it like it were NumPy. And then, can it just go away? Yes, it can just go away. And then the rest of this is a formula. This delta x squared, oh no, again, I'm assuming that you can see my highlights, and yet you can't. This delta x squared, where my mouse is going around, and this delta y squared, they're added. There's the plus. That's inside a square root. Okay, last part is you have to sum over that length. Ox sum, axis is -1. -1 is the deepest axis. So like if you had a 3-dimensional NumPy array, axis 0 is the first dimension, axis 1 is the second, axis 2 is the third, or you could count from the other end. -1 is the 3rd dimension. So it's a sum over the 3rd dimension of that square root. That's it. And I think this notebook is not working anymore. Maybe it was just the kernel that died, I don't know. Oh, no, it didn't die. There it is, it's working. And that's the result. So it becomes this rather easy one-liner. Not easy. No, I don't want to be saying things like that. It becomes this rather concise, that's the word, this concise one-liner. And where we started with all of this at the beginning was APL, how they made this super precise language, this mathematical notation, and it got to the point where it was so concise that it was very difficult to build these things. And when you have this success at the end of the night and your program runs, you put it on a t-shirt and it's just garbledy-gook. Well, this concise thing is readable, I hope, and I'm going to say that, and I'm going to hope you agree and invite criticism. Is what I'll say. That after you see that, maybe it might have been difficult to get to this. Maybe it's less so when you've been doing this for a while, just like when you just started with NumPy. But when you see that and you are familiar with NumPy, I don't think there should be anything mysterious about this, right? Because there's your delta x, and there's your delta y. And pedagogy, I should have made them separate variables. Break them out into separate variables. But yeah, then the further exercises are doing things like not going over all the paths, but like finding as the crow flies distances. And I just had a lot of content there in case we zipped past things. But actually, we are just perfectly on time. This is exactly where I wanted to end. And so you can catch me after. We'll be going to wherever we're going next. That's where I'll be. And if you want to talk, I'm very open to that. Questions right here after this too. And if not, if we're going separate ways, thanks for coming, and have a good day. Have a great conference. Actually, I did this problem and solution first. So the pedagogy got better as I was writing more. I was working backward.